We are the Gujarat Technological University. Since its inception over a decade ago, GTU has been empowering young and curating minds to realize their true potential. Over 4 lakh inspired students are enrolled with one of the premier academic universities in India. With more than 450 affiliated colleges in its fold operating across 5 zones of the state, GTU, the International Innovative University, your place to move forward.
Hello dear students, today we will start with the new topic, that is hot probe method. We all are aware with the major 2 types of semiconductors, that are N-type semiconductors and P-type semiconductors. So is there any technique available scientifically from which we can prove that the given material is of N-type or P-type semiconductor? So the answer is we have hot probe method, which easily distinguishes between the N-type and P-type semiconductors. The hot probe experiments provides a very simple way to differentiate N-type and P-type semiconductors using a soldering iron and a standard multimeter. So how is the experiment performed? The experiment is performed by contacting a semiconductor wafer, that means a semiconductor layer, with a hot probe such as heated soldering iron and a cold probe. So basically here the 2 probe method can also be compared because the hot probe and cold probes are used. Both probes are wired to a sensitive current meter. So it is a very simple experimental setup. The hot probe is connected to a positive terminal of the meter, while the cold probe is connected to the negative terminal. So I hope that the experimental setup is clear in your mind, which can again be detail explained with this experimental setup as shown in this figure. So T high suggesting the high temperature probe, T low suggesting the low temperature probe, and both are connected to the wired current ammeter, and capital I is the symbolic representation for ammeter. Current is flowing from the high temperature to low temperature as the simple physics phenomenon. When applying the probes to N-type material, see, this is very important, one obtains a positive current reading on the meter, and if you are using a P-type material, then the sensitive current meter will deflect the negative current on its reading. A simple explanation for this experiment is that the carriers are moving within the semiconductor from the hot probe to the cold probe. See, the carriers mean if you are considering the P-type material, the majority charge carriers will be holes, and if you are considering the N-type semiconductor materials, then we have the electrons are as major charge carriers. Very simple experimental setup and a very easy explanation, but an important question in view of your GTU examination. While diffusion seems to be a reasonable mechanism to cause the carrier flow, it is actually not the most important mechanism since the material is uniformly doped. As we all know, all the semiconductors have intermediate values of their conductivities between the conductor and superconductor, or we can say insulators. So until we dope the semiconductor, we can't get the improvement in their conductivity. So here they have mentioned that the diffusion seems to be a reasonable mechanism to carrier flow. Assuming that the current meter has 0 resistance, because any electrical component has its own internal resistance, but for a sense of time we consider the current meter has 0 resistance, and we are also ignoring the small thermoelectric effect also in the metal wires, which is always there, but for the sake of time we are ignoring it. So with these two assumptions, one can justify that the Fermi energy level does not vary throughout the material. Means while performing this experiment, you will have no change either in the conductivity or the resistivity of the given semiconductor or the investigated semiconductor. A possible energy band diagram is shown in this figure. As we all know, the EV is the valence band energy, EI is the intermediate band energy, EF is the well known Fermi energy, and EC is the conduction band energy. The horizontal axis represents the temperature, vertical axis represents the energy band. So with the decrease in temperature, we can see a slight bending of conduction, intermediate, as well as the valence band. But the important thing which we have to focus is there is no change in the position of the Fermi energy level. This energy band diagram illustrates the specific case in which the temperature variation causes a linear change of the conduction band energy as measured relative to Fermi energy. As the effective density of states decreases with decreasing temperature, one finds that the conduction band energy also decreases, as can be depicted from this figure. With decrease in temperature, the conduction band energy also decreased. Moreover, it results into the electric field which causes the electrons to flow from the high to the low temperature. As can be seen from this figure, the red icon reflects the motion of electron throughout the energy band, and as the energy decreases, the temperature also gets decreases. The same reasoning reveals that holes in a p-type semiconductor will also flow from the higher to the lower temperature, as can be confirmed from the valence band energy. Thus, this important mechanism can be used to determine the current density function using the expression given in this presentation, that is J is equal to mu n into n inside the bracket delta EF upon delta x minus QP del T over del x. So mu n is the number of charge density of electrons in n-type semiconductor, small n is the number of majority charge carriers of electrons in n-type semiconductor, EF is the Fermi energy level, x was the again horizontal axis or the position of Fermi energy level, q is the charge, rho is the charge density, or we can say the resistivity, as we have seen the dependence of electrical resistivity on the carrier density in our previous lecture. T is the absolute temperature in Kelvin, and x is again the position, where the q rho function means charge resistivity function is given in the expression number 2, that is q rho is equal to minus k is the Boltzmann constant, into the bracket 5 upon 2 minus T upon mu n del mu n upon del T plus natural log of Nc upon n, the number of charge carriers in the conduction band, that is Nc, divided by small n. So we have seen that the position of electron as well as the energy of electron or conduction band and valence band differs after the temperature variation. So how this will affect the current? The current will increase with doping. That is absolute reason, because when you are adding some impurities into the semiconductors, the conductivity is about to increase on a linear manner. And applied temperature gradient, since semiconductor does not become degenerate or intrinsic. Intrinsic means a semiconductor without any impurities within the applied temperature range. So this way we can distinguish the two types of semiconductors, and this was the measurement technique number 3. Already we have discussed 2 probe, 4 probe, and now in this particular lecture we have gone through the hot probe method. Thank you for visiting this lecture.